Hello, everybody. My name is Pablo Garcia Salaverry, and I am assistant professor at the Fluid Mechanics Research Group in the Department of Thermal and Fluids Engineering at the University Carlos III of Madrid. I will present you the work entitled Mesoscopic Modeling of Porous Media with Application to Electrochemical Devices. The case of gas diffusion layers and proton-exchange membranes. Well, this is the outline of the presentation. First, I will give you a brief introduction to electrochemical devices and porous media. Then we will focus on the model formulation, the coupling of macroscopic and microscopic models. Then I will show you results regarding gas diffusion layers. We will discuss single and two-phase transport. And then we will focus on the proton-exchange membranes, in particular, how we model conductivity of membranes using a percolation network. And finally, I will give you the conclusions and future work. Well, okay, so something here on the left, we have several electrochemical devices such as lithium-ion batteries, redox flow batteries, fuel cells, and electrolyzers. And something that is common to all these electrochemical devices is porous media. So here on the right, we can see we have gas diffusion layers, which are present in fuel cells and electrolyzers. In all these devices, we find membranes to separate the compartments and allow the transport of ionic species. Then we have macroporous electrodes, which are rather similar to gas diffusion layers. We can find this, for example, in redox flow batteries. And also we have catalyst layers, like in fuel cells and electrolyzers, where the electrochemical reactions take place in these two devices in particular. Okay, so there are several porous media. They play different roles in electrochemical devices, and modeling them is essentially a multi-scale problem. Because, well, here we have the different scales of modeling in engineering. So we can find from electrons to the component, the level, and then finally we will reach the application. So in terms of modeling of porous media, we can put on this scale, we can put different techniques. So we have here the pore-network modeling and direct numerical simulation. This will be at the component level. So we saw for the detailed transport in the components. For example, pore-network modeling is a usual practice to improve the prediction of two-phase transport in the porous media present in electrochemical devices. And then also we can use direct numerical simulation, combining tomography images with continuum modeling through the pore space, or even can be the solid phase if we are interested in electrical conductivity or thermal conductivity. Then we have in between, we have hybrid modeling, which is the one we are focused today. Okay, this is like an intermediate level between these pore scales techniques, and then macroscopic modeling. Macroscopic modeling using macroscopic effective properties to represent the porous media. These techniques are best suited for large scale simulations, and when we are concerned about the the modeling of the cell or even the stack. But here we focus in this hybrid modeling, how we can incorporate into macroscopic models also a better representation of the heterogeneities caused by the porous media, and how we can improve also the modeling of the two-phase transport. Okay, so we will start with gas diffusion layers. This is the work is mainly focusing polymer electrolyte fuel cells. And this is our modeling approach. So we have the macroscopic model. This is, we use a control volume mesh. So as you can see here in this picture, we have two constructive elements. We have control volumes, which are, we have, in this case, this is the pore size distribution. So we have a different pore size for each control volume. And inside each control volume, we can have different or several computational cells. And then in between the control volumes, we have what we call the connectors, which is physically in terms of the mesh is the, well, are the phases between the two control volumes. Okay, so in this particular case, we have here these two phases in two edges in 2D here between this control volume and this control volume. So this is our mesoscopic representation of the GDL. We don't have the detail of the detailed microstructure of the porous media, but we are not at the macroscopic level saying that there is a single effective property for that characterizes that porous media. Okay, this is important in thin porous media when we have a finite thickness to include the heterogeneities where we have in the layer. So okay, we have this representation. And then inside each control volume, what we include is, well, this is the microscopic model. We include a pore-network representation of the porous media. Here we are using a structured pore-network, which is embedded into the control volume mesh. And we use that pore-network to compute the local effective properties. Okay, so we are going to couple the pore-network and the control volume mesh through this local effective transport properties. Okay, so well, to generate the pore-network, we use well, the standard methods. Here you can see the procedure. Okay, so we start with a uniform distribution of cumulative probabilities according to and we assign pore sizes according to the experimental pore size distribution of the material. Then, well, in this case, in order to capture the anisotropy of these materials, we include a convolution filter. And finally, we go back to the uniform distribution of cumulative probabilities. So we are not altering the pore size distribution of the material. Okay. So well, this is the standard practice, and finally we reach this result. How we compute local effective properties here, I am focusing on local effective diffusivity. So essentially, we have species conservation. So in this case, is for transport in the y direction. So we have two throats and we have one pore. So the flux coming through this throat and this pore and this throat, they must be the same according to mass conservation. And finally, we can combine this equation into a local effective diffusivity. Okay, which characterizes the diffusive resistance of this pore or this control volume pore throat representation in the y direction. Well, you can see that the result that we reach is for is similar to the harmonic average of the conductivities. Okay, so this is classic result from pore-network. Okay, so okay, we have this way to calculate the local effective properties. We can do this in the y direction, but we can also do other directions in order, well, to have the anisotropic local properties of the material. These are results for dry conditions. Okay, so this is diffusion. Here, essentially, what we have diffusion and also some results for hydraulic permeation. So this is the pressure distribution. Okay, but here I will only comment on concentration. So this is a simulation in the through plane direction. We impose Dirichlet boundary conditions for concentration in this phase, on this phase and this phase. Okay, so and we reach this this concentration, the distribution through the material, and this is the same when we impose the concentration drop in the in plane direction. Okay, the material plane. And this is what we get. This is the distribution of fluxes at here at this outlet surface, and you can see that well, there are strong variations of the diffusive flux. For instance, there is one order of magnitude of difference there between the minimum and the maximum value of the diffusive flux. So this is important in electrochemical devices in order to study the effect of these heterogeneities on the durability. This is something we are working on now. Also, another improvement we can make with this hybrid modeling is two-phase transport, improve the prediction in terms of two-phase transport. Essentially, they are what, as I mentioned before, we use the connectors we use them as interfacial valves. So they open and close depending on the capillary pressure we have in adjacent control volumes to that connector or those faces of my control volume mesh. So here you have some result for capillary pressure. Here we have the different gas diffusion layers with different compression ratios, and you can see that we are we have good agreement with experimental data. We can also model invasion percolation, and even we can do evaporation condensation. So this is in particular evaporation condensation is ongoing work, but with this representation we can improve a lot the predictions in terms of two-phase transport compared with macroscopic models. So this is important for material design, for example, in order to provide a good modeling of the two-phase transport for in fuel cells, for example. And then finally, some results in terms of gas effective diffusivity under two-phase transport, two-phase conditions, sorry. So here we have, this is the relative effective diffusivity, and we have different average saturations in the porous media. Well, you can see that we follow a power law of the form 1 minus s to the power of 3. Well, this exponent, this saturation exponent of 3 is in agreement with previous experimental data. I would like just to emphasize the importance of the peak saturation here. No, if we have here the injection phase, here we usually have much higher saturation near this injection phase compared to the opposite phase. So these bottlenecks that are created due to the accumulation of water near the injection phase are important in order to capture the 1 minus s to the power of 3. Okay, so and we can here, for instance, we are combining the modeling of two-phase transport with gas diffusion. Okay, so we can do this combination of modeling in a very straightforward way with this kind of modeling. And okay, then I will focus on some results for membranes, also with application to polymer electrolyte fuel cells. Okay, so here we have, well, we adapt the model. So we have the percolation. Now we have a percolation network. In this case, we use only one computational cell per control volume. And then we have homogeneous local conductivity. We are not computing local effective properties. Okay, so we have homogeneous conductivity in those sites that are conductive. And then between sites that are conductive and those that are non-conductive, we have no flux boundary condition. Okay, so essentially in our percolation network, we have 3 types of sites. We can have material that is completely dry, so this is no non-conductive site. Then we can have some disconnected weakly hydrated or non-hydrated sulfonated sites. So this will be also non-conductive sites, essentially because they are even if they are sulfonated, they are disconnected from the water network, which is providing the ionic cluster for transport of protons, in this case for the conductivity, the transport of protons through the membrane. Okay, and to model, for instance, the proton transport, we use the Nernst-Planck equation, which is simplified to the migration term. So here we have, this is the bulk conductivity we have in the conductive sites. It's given by this expression in terms of the mobility of protons. And okay, and then we have that the no flux boundary conditions between the conductive sites and the non-conductive sites. Okay, so we are using this modeling approach. And then, okay, here we have some results with these are experimental data extracted in the lab. These are for the membranes with different sulfonation degrees. Here we have the ionic conductivity as a function of relative humidity. Okay, so these are the experimental data, and here we have the comparison between the numerical data and the experimental data. So the black are the experimental data, and the color lines with the symbols are the numerical results. So you can see that there is good agreement between the model prediction and the experimental data using this this modeling approach. Okay, where we have a percolation network, but we are solving continuum equations. Okay. In our mesh or in our, say, percolation network, this hybrid modeling approach. And finally, a result that I would like to emphasize is the importance of the tortuosity in the conductivity. Here we have a plot of the tortuosity as a function of the relative humidity. And we can see that for those membranes that are, well, that have a higher sulfonation degree, well, we are decreasing the tortuosity. We have a lower tortuosity, but also we have higher conductivities at lower relative humidities. Okay, so this is an important point in order to design high performance membranes for fuel cells application. where we would like to have a high conductivity, or say acceptable conductivity at low relative humidity. Okay, so well, the conclusions of this work are that a hybrid pore-network continuum model has been presented. The model accounts for microstructural heterogeneities while keeping computational cost moderate. We have a more realistic description of two-phase transport using this approach. And this is a versatile approach to model thin porous media in electrochemical devices. Okay? The possibility of solving continuum equation, but at the same capture the discrete effects and the effect of the microstructure at mesoscopic scale is important. It's important in these devices, and to study, as I mentioned, issues like durability or two-phase transport. Also, the interaction between porous media and the flow field. These kind of things it is important to have all these ingredients there. And then as future work, we have implementation into a multi-physics fuel cell or battery model, analyze effects on performance and durability, development of open source code version of this hybrid modeling, and combine it with machine learning in order to material design. Okay, so we can improve properties and finally improve performance of electrochemical devices. And also some ongoing work that is now we have include the pore size distribution into our percolation network for modeling membranes. So we can include, this is a working collaboration with Minya University in Egypt. So we can include the distribution of the sizes of ionic clusters, and well, compute local conductivities, and improve the prediction and account for those heterogeneities of the membrane material. Okay, so well, thank you very much for your attention. Here you have well, my website at the Fluid Mechanics Research Group, and also my personal website, and this is my email. So thank you very much for watching this video, and I see you at InterPore. Thank you. Bye.